Hello guys, welcome everyone. Welcome to the next week of Raku Weekly Challenge. So today we are going to look at the task number 1, Fibonacci sum of week 76 of the weekly challenge, and let's read the task. The task is you're given a positive integer n. Update. Write a script to find all possible combinations of Fibonacci numbers required to get $n on addition. You're not allowed to repeat the number. Print 0 if none found. So the example, for example, the input number is 6 and output should be 1 plus 3 plus 2 plus 3 or 1 plus 5. Both 2 and 3 and 5 are Fibonacci numbers, well, including 1. And for the number 9, there are also two options. Here they are. You see, so we cannot repeat the number twice, unlike the previous week where we have, where we actually, for some cases, we had to repeat them. Okay, so that's clean. Well, the only thing that probably you will never print 0, because if n is not 0, you can find at least one combination. If the number itself is already a Fibonacci number, then it's the minimum number which you can give in the result, which is 1. For all other cases, there will be a combination. Right, so let's look at the solutions. Immediately, we go to the Raku solutions. Yay, please do. Links don't work. Right, so the Raku solution. The first solution here in the list is again the Raku solution by Arne Sommer, Raku number 1. And here it is. So we take the positive number, the positive integer number, which is positive and an integer, so depending on the settings, probably again we're going to print the steps, or if it's up to is not set, then we're going to go to Fibonacci decomposition procedure straightforward. Right, so Fibonacci, so the target number, Fibonacci sequence. So this is the way to generate the Fibonacci sequence using the sequence operator, 3 dots. Basically, it's a lazy thing with the, there's no end here. And this is the rule how we generate. Basically, this is like the definition of Fibonacci numbers, right? The only thing to notice here, apart from this beautiful thing, is the way the way the sequence is bound to the variable, to the scalar, instead of just assigning to. Actually, I would just assign it to like at fibs equals and all that without parentheses. Right. So then for Fibonacci, so we are looping over those numbers. Well, in theory, we will never stop. So we'll take this fib. So this is a pointing block, basically the body of the loop. And for this Fibonacci number, we are going to execute this one. So we will stop if the current Fibonacci number from the sequence is bigger than the target. So that we do not loop infinitely. And we push. Well, on shift, actually, we add the current number to the beginning of the fibs array. Right, so basically in the fibs array, we have the Fibonacci numbers from 1, actually including 1 twice, right? So 1 is included twice here at this moment, up to the target number. And actually, if Fibonacci number is bigger than target, then we stop. So if the target number is a Fibonacci number already, so we will have it here. Okay, so then we call the recurse function, and the recurse function, actually it looks like the function from the previous week. So we start with 0 and an empty result, empty values, and so if the value is less than input, so if we didn't manage to combine the number, then we scan all the Fibonacci's numbers and we take the first one, right? Because this was adding to the beginning, and we started with the small number. And right, so we started with the smallest number, and basically this is the smallest number, if I'm correct. Right, and then we just try to add this number and test if we are still within the limits, and if we are, then we recursively call the function itself again with some modified input data for this function. Okay, so let's just run this program. Raku Arne Raku chair 1, like number 9. Right, there are two options. So what was the task? The task was find all the combinations, right? It's not like find how many of them are there. Okay, 1000. There should be like about 15 things. Yeah, so yeah, this is the most compact representation of the number, decomposition into two prime numbers already. And after that you just well, basically the idea is just you've got this minimum thing, and it's called the Zeckendorf sequence. These are the biggest possible Fibonacci numbers which can add up to 1000, and all the rest is based on the previous thing. So you see, so 987 repeats 3 times here. After that it's split into 2, then again this 610 is keeping like, yeah, until the end, but we split 377 and so on, so on, so on. And also here like 13, first it was 13, but then it's split into 2 numbers, and then the one of them is split again into, like 5 is split into 3 and 2, and so on. So yeah, and you have to repeat this procedure again and again until you reach the end. Good. So this is the solution. So it is the algorithm does not test anything. The only test is just if we reached the desired number, but it's not like trying all the combinations, right? Right. Good. Okay, going next. Feng Chang, the new name, at least for me. Here is the solution. So we start with the integer number. In the input, we generate the Fibonacci numbers, and you see, so we start with 1 and 2. So we... yeah, by the way, in the Arne solution, we had this 1 and 1 as the first 2 items of the Fibonacci sequence, but we didn't see any ones, any additional ones here. What if, like... So yeah, 1 is not repeated. It should be 2, right? Okay, yeah, that's good. So, but here, because we cannot repeat the Fibonacci number by the task definition, so yeah, we just can generate a shifted Fibonacci sequence without the first one, so that all numbers in this sequence are different. Right, so here's the number. I don't know why we need to copy that. Actually, where are we using this num? Yeah, it's a global thing. But are we using this? Yeah, so we use it to just print. Okay, then we just call directly this function, and again this is, you see, so this is the recursive function, and actually it's double recursive. So we pass the Fibonacci numbers in the new array, the empty array, so to collect the result, I believe. If the number is 0, it's not our case. If there's no Fibonacci numbers, probably left, right? Because, yeah, I see, so here it is. Then, if the number is less than the first Fibonacci number, so yeah, we cannot do anything with that. And basically, that's the result, right? Or not? Probably this is about the weird case, right? Which should not happen. Or maybe it can happen. Right, then, F Fibonacci numbers, N the result. So we add to the result the first Fibonacci number and repeat the procedure for the alternate. Yeah, so we subtract this number from the target number and we call the procedure again, but after that we call the procedure for the original number with the same set of Fibonacci numbers and with the result. Yeah, I didn't quite understand those lines, and especially like these, this is a bit difficult to understand, right? But nevertheless, let's Feng Raku chair 1 and number 9. So the simple number, right? It works. And what if like 1000? So we know the result. Well, yeah, it appears in different order, but that's not important. The important thing that it looks like the same number of combinations were found. This is the thing that time. So this solution looks like it just straightforward. It's only subtract, and so on. So until it finds the result. So unlike like my solution, we will see it a bit later, where I just try to find all the combinations. Okay, so we're going to the solution by Jason Messer. Oh wow, yeah, so here is the solution with the combinations which I just mentioned. So we start with, yeah, okay, so we have these two numbers, and what we do, so we accept this positive integer. We again bind the scalar to the sequence of the shifted Fibonacci sequence. You see, so it starts with 1. I don't know why we need this. Probably just to be able to call this. Yeah, interesting. So we see, so this is a block, and I don't understand how that works. So what this means is, okay, so this is, okay, maybe let's just, okay, so let's see, so, oh yeah, so yeah, it still works. Right, so it's more than 1 minute. Okay, so what happens here? So I have this, right? Okay, I cannot have this. I need first to define n. Okay, for example, 100. Then I have this. What is a? You see? So this is something. A, for example, of 5. A of 10. A of 1000. So nothing changes. So I don't know what actually this means, because I could understand if A is this, right? So this is the placeholder variable, which doesn't work because wait, ooh, this is more difficult than I thought originally. So we see, so there are 2 stars here. Not quite clear why we need that. So A equals 1 to star plus star dots star bigger than this. This is what I meant. You cannot bind operator with this left hand side. Right, so you need a pointy block. So yeah, basically, what's the point of having this here? Because for 100 we got the result up to 100, right? Not bigger. And this actually changes nothing, if I'm correct. So yeah, I think this is a bit strange. But okay, nevertheless, the main thing is that then you just take all those numbers up to the number, this n. Actually, yeah, this n is not used because this one is already fixed, so it's not an argument of anything. So you take all the combinations of those, all the combinations of different lengths, so starting from 1 and ending with the whole set, well, the whole list. And then you just grab those combinations which pass the condition of where the sum is the number. And so these are the combinations, and then you have this for loop, and inside this for loop you have this body with the pointy block. Now this is the real argument. So this is the solution, and see, the solution will give you the sequence, right, or the list of the sequence. Oh my god. Right, and then you just print it. So let's run this function in a separate window, like here, and just, well, yeah, first of all, let's just Raku t like 100. Yeah, yeah, of course. Yeah, let's modify this args 0. It's difficult to type this thing. Okay, so now it will take the number. Oh my god, oh my god. What is it? Yeah, we cannot. Type check failed in binding to parameter $n, expected in but got string. Right, so we have to convert this to an integer. So these are the combinations for 100. See, there are no repeated ones here, yeah, because we only have it here. But I wonder what this is. Say solution what? This is list, right? So yeah, the only thing I don't understand if you can do it like that. So yeah, you need it. Yeah, so this one will work, right? There's nothing changed, so you don't probably need this at all, and you don't need this, and maybe this one is also like, why the previous two, just the current, right? Yeah, it's the same result and less letters. Right. Okay, good. So probably the thing to notice is this dot sum, which is called on the dollar underscore. Yeah. We can go next. The next is... So it was Jason, right? Who was that? So Jan Krnavek. Here is the solution. The solution is... Yeah, it starts here with the main function. So you need the test flag. You have to have it. So then you wrap the thing if you're going to log. We're not going, so we can skip this. And then, yeah, basically fib sum, you map. So yeah, these are the tests. So the result that you want to achieve, you expect to achieve here. And you see, so something is returned with the, like a hash with the, well, actually it's not a hash probably, with the used field in it. So okay, so let's look at the function fib sum. Fib sum starts here, so it takes the target number, right, the sum. Stop index, so we know where to stop. So we are looking for the first Fibonacci number, which is bigger than the desired number, and this k flag asks the first method to return the key, not the value. Right, so okay, so then you take the Fibonacci number, and then you do with that. So yeah, basically this is just the way to call the method on that. Is it? And check if this Fibonacci sum number is non-zero thing. Where does it come from? Okay, so this is a constant of okay, so Fibonacci. Okay, Fibonacci numbers. This is the shifted Fibonacci number, Fibonacci sequence, infinite lazy sequence of shifted. Again, one is only so the first two numbers are 1 and 2. Then, yeah, there are some captures again. Oh, what is it? So there's the sequence, next level cache. The next level is the map which calls the iterator, which is this multifunction. Why is it multi? It appears only once. With the capture that takes the target number, the positions, right? Because I believe this is the position, right? And the used thing. Okay, I don't understand this. What I can only do, I can just run it. Bosh, not here. Okay, not here. Raku, Raku. So one. So there are a couple of built-in tests. Rakai not found. Right. So we need to do it like that. Okay. So all those numbers passed the thing. I want to see what's there inside. I'm not satisfied with just printing. So okay, so fib sum of 100, 1000, and I believe I want just to print this, right? I don't want any tests. I believe this will work. Raku T. So there are no, oops, I believe something went wrong. Okay, because I need to do it like used, right? Will it work? I mean, not here. So, and this used is collected here. So right, so this is a capture. So this is what I told you, this is not a hash, this is a capture. And in used we just collect something. It looks like the program. How can I do that? The program in Prolog looks like this. Right, okay. Maybe 1000 is a bit big, but yeah, here are the combinations. They look correct, which is good. Good. I don't understand the solution, but I see that the result is correct. Going next, so it was Jan Krnavek. The next is solution by Mark Anderson. Alright, so here's the solution. So it has two multi-sub main functions. So two versions of the main function, which is, one of them is defined for numbers within the range 1 and 2. Basically, for two numbers 1 and 2, we can actually try to use, for example, vertical bar here and create a junction instead of range, again, one character. So for these, the result is directly the number itself. Okay, that's a trivial case. And a more interesting case for other numbers, we get first Fibonacci sequence from 1. Actually, this is the shifted sequence because there's only, it starts with actually the official second number. Then this thing is a bit tricky because, well, yeah, I think it's redundant actually, because star plus star, what is that? Actually, that's the next Fibonacci number by definition. Here's the definition, right? So we can leave the star alone, and maybe we can put the hat after here, after the 3 dots here. Maybe we can play with this equal sign just to get the result we want. But nevertheless, I found this a bit strange, at least. And right, nevertheless, okay, so we've got some Fibonacci numbers up to the $n. After that, we are gathering the results into the @results array, which we are going to print after that. And what we are gathering the sequences, right? Different sequences which actually give the desired result, whose sum is n. And so we start with 2, and this $n, it's the length of the combination. So we try to create all different combinations of different lengths. We ignore the combinations of one character for some reason. Actually, what is $n is already a Fibonacci number. We will not return 1, right, in this case. But okay, it's a bit vague in the task. Okay, so but here, so what we do, so we start from 2 up to the whole length of the Fibonacci sequence of our Fibonacci sequence, which is less than $n. So we start like 2, 3, 4, 5. And we generate Fibonacci sequences. So yeah, basically I think it's a bit okay. So let's do it like this. So here, like Raku, my n is 100. Then we define the Fibonacci sequence, right? It's right below 100. Then we create some Fibonacci combinations of 1. Actually, we don't have these combinations of 1, right? We only have combinations of 2. Then we got combinations of 3 and so on. So, right, the combinations of 3 gives us the list of the sequence of lists that contain 3 elements. But the thing is that we are going to increment $n, and we are still taking the combination, so one of these in parentheses. But basically, you don't need, right, that. You don't need that loop because you already, well, except maybe with an empty list, but we will still ignore it because there's this grep. So we can just do that. We don't need, well, if you don't want the combinations of 2, you can just probably do it like this, right? You start with combinations by 2, and you end up with the combinations that include all those numbers from the fib array. So I believe this list is redundant. And maybe another thing that you have to understand is that this is $_, this is the scalar, but actually it's not like a one single number. That this is this combination, right, which includes, actually in this program it never includes one number, right? The minimum is 2 already. Okay, now good. So but let's run this program. Raku, Mark Anderson, Raku 1, and we are given numbers 1000. Right, so this is the minimum combination. So yeah, it looks like a correct solution. The minimum combination is 2 numbers, which are both Fibonacci numbers, and all the rest we start further. Okay, good. Going next, and we go to the solution by Markus Holzer. Right, here it is. So Markus said that his solution is 500 times faster than my solution. So yeah, it's see, so there's an example for this big number of 9 characters. the result is computed in just under 10 seconds, and this is the number of combinations, and that's why the Zeckendorf representations actually tab was open from the beginning. So the idea is that you can express the Fibonacci, any number as the sum of Fibonacci numbers, which are all different. And there's some algorithm how you do that. Basically, you just, for example, this number 100, and you just take the biggest Fibonacci number, which is less than 100, which is 89 in this case. And after that, yeah, you repeat the procedure for that remainder. Yeah, and that's it. The only thing that in our task, we need all the combinations. And basically, so here are the shortest sequence of two numbers, but then I have to basically create repeat the procedure for one of the numbers, like here. Then you do it for the second number, and basically you, yeah, again, you can split this number into other Fibonacci numbers, and so on, so on, so on. The only thing that in the long solutions we don't have to have repeated numbers, because if we will just go straight and split it over the summands, then we end up with the same numbers more than once, right, in the sequence. So we have to filter that. And right, let's go to the solution so we can close this one. The thing is that this solution also uses is cached trait, which is unfortunately still an experimental feature. And you see, so there's this is trait here and is trait here applied to the functions, and this thing should skip evaluating the result if we already saw this, if we already did it earlier, if we already called the function with the same number. So yeah, basically when you split, like for example this 233, you should already use the result which was obtained earlier, or somewhere else, right? Like this 377 is here and here and here, and yeah, it's the same result if you will start calling this function again with this number. Okay, then yeah, start just for measuring time. We're not interested in that at the moment. With my combinations is gather, combine, Zeckendorf, $n, and some block. So I wonder, so with, it looks like some kind of if right here. So if this one exists, it exists, and if it's defined, so basically if it contains some numbers, right? Probably if can be used here, if I'm correct, but never mind. So what we have here, we have gather, combine, Zeckendorf. So there are no parentheses here, but actually these are the function calls. Combine is here, and Zeckendorf is here, and $n, basically this is passed here. And the result of Zeckendorf is the thing that we pass as an array to combine function, right? And after that we have gather on that. And this gather actually, so we see, so there's gather here, there's no take here, but there's take here, right? So this take thing gives us a new item to the sequence which we are gathering here. Also, like there's a gather and take here, but these work together, so they have no effect on this gather. Well, no direct effect. Right, okay, so we probably have to start with this Zeckendorf function. Zeckendorf $n is cached, right? So we generate the sequence of Fibonacci number, and its state, it's already kind of cached thing inside the function, right? I don't know why we need square brackets. Then there's some function, I believe, right? So if the input number is 1, we immediately return 1 as a list. So this function should always return list according to this. Otherwise, we call this, and this is eager gather 4. So yeah, we eagerly gather something 4. So we grab the Fibonacci numbers, these numbers, right, below n. We start with the biggest one. Actually, I think that this one can be made even more efficient, right? Because we don't need to grab them. We can just immediately point to the position where this number happens, right? We can find from the right end, from the end of the array, we can just find the number which is less than n, and we know that all the other numbers on the right side other numbers we want, then we can reverse that, especially if we want to start with bigger number. But okay, so we start with the biggest number. If this number is less than n, or is n already, we take this number and we decrement n. Actually, yeah. Okay, yeah, but still, yeah, still the thing probably can be become more efficient. I don't know actually how important that is, because Fibonacci sequence is not that long, even for bigger numbers. Okay, and we decrement the number. So from 1000, we subtract number 987, and we have 13, which is the next n, and we repeat the procedure. Okay, after that, so we gather those Zeckendorf representation here, and we pass it here to the combine. Right, so what do we do? So there's this valid function, anonymous function with the signature as a scalar, So where are we using that? So there's another one, insert. Okay, so the main body starts here. So we're taking and sync. Sync basically means that evaluate and ignore the result of everything, right? But still do not ignore the computation process. So at Z is the input, basically Zeckendorf numbers. So we take and sync. Take that, but do we do something with that, or either we just take it immediately? So map, so we map it to Zeckendorf representation. It's actually a function. So for each of them, right, this is what I said, for each of the numbers from that, so this is the sequence, right? So at z dot map dot kv dot map and all the rest. So we're calling Zeckendorf function for each of the elements in at z, and we find the representation for those things. Then we apply to the result. KV gives us the indices in the values. Then we map that to this, insert. Then we grab if it's valid, and combine. We call this function basically recursively again for those numbers which pass all those, basically which pass this filter, right? If it's a valid number. What is a valid number? Yeah, I don't know from where to start. Well, let's start from insert. So from where to and what? Where, insert where and what? So we take a copy of the Z. We splice it. Yeah, basically we insert something into this position, I believe, right? Then valid thing, if its number of elements is the number of elements of the, so yeah, basically if we have all the elements, if all the elements are unique and the result matches the original thing, and the result actually is inside this, right? Well, not actually, not, and the result does not repeat the at z. Okay, yeah, I kind of understand the whole picture on a bigger scale. Not like I don't quite understand this. Well, yeah, only the idea. But yeah, so yeah, here we passed actually valid. It's not the sum is n, but validness means that there are unique elements only, and those elements do not echo the original data, right, that we got for this function. Okay, but still, then we still want to combine those. That's a highly recursive algorithm. But let's run that. Raku, Markus, Raku, oh my god, 2 1000, and it doesn't work. What was that? Challenge. What? Right. Input file. Oh my god, it's number 1, right? Yes. Right, so number of combinations is 15. So here we have all those combinations. Yeah, unfortunately we don't see the combinations, but that's well, that was not asked, right? And yeah, so I believe for 10,000 we'll get about like, wow, really, even not 10. So, wow, that's really fast. So you see, so yeah, we are still within within even half a second. Just quarter of a second for one. Oh, yeah, okay, let's make it 1 million. And I believe we will still are like close to a second. Good, really good solution. Yeah, I wonder if we can make it faster. Still using Raku. Actually, for Raku, wow, that's actually so we've got the Raku programming language, the Raku the compiler, which is kind of slow, but we still got. And if for example we'll get this put into module, and we can gain even on compilation time, right? Wow, that's cool. That's cool. Okay, right. Going next. So yeah, so as a homework, you can just create the module, put this code into a separate module, create the one-line program which uses the function from that module, and yeah, the first time you run the program, it will compile the module, put it in a separate file with already compiled representation of that file, of that module, and the second run will be even faster. Okay, Pearl 6 Steve. Right, so this is what happens when you use the name of language in your, right, so in your nickname. Right, Raku number 1. Good. So we take the number and its required number. The answers is okay, so we just it's basically one line, right? So we generate the Fibonacci number and we start with we ignore the first number. Actually, we could just ignore it here and put 2 here instead of that, but that's also a possible thing. Slice off the duplicated one. Then we generate all the combinations. All combinations are including combinations of one number, of 2 numbers, and up to basically the length of this. And yeah, and so see here you see that, yeah, the sequence, there's a hat here, and there's 1 star, and there's the equal sign. And after that, you grab the thing, right? So this is a very clear and straightforward solution. Straightforward in that sense that you can just directly get the answer without evaluating that. Right. Let's run it. Raku P6 Steve, Raku Ch1 1000. And here are the results. Good. Going next, the next solution is by Shahed Nushmand, Raku number 1. I believe this is not finished. I cannot run that. Yeah, okay, let's skip that. Simon Proctor, Raku number 1. Okay, so we take the number, unsigned integer. We get those combinations, which, okay, so the Fibonacci sequence unique. I believe this is a bit redundant because it will only remove a single number from the sequence. Combinations, grab. Okay, so yeah, basically $n is, so yeah, so here instead, unlike previous solutions, we have the pointer block, which takes the numbers from the current combination at C, and we compute the sum by using reduction operator with a plus inside, and we compare it to n. If there are some numbers, we print them. If not, we print 0. Yeah, probably some people just forgot that we have to print 0 if there's nothing. Simon Proctor, Raku, but can we just print the... yeah, so because we want to print the combinations themselves, right? Ch1 Raku 1000, 100. Let's do it by 1000. But I already see that everything is correct. Good. Right. My solution, Raku 1. Yeah, basically, you won't see anything new here. So I take the number from command line, I create the Fibonacci sequence, then I make some output for combinations which pass this. Right. So simple. Yeah. So I think this is a bit simpler than like in previous solution, but nevertheless, Raku Ch1 1000. These are the solutions. why it was so slow. Yeah, see. So it yeah, because in Simon's solution we print the array which already was prepared, and in my solution, yeah, I'm printing this as soon as I find the next element, right? And I'm not waiting for the, and it visually looks stranger than this solution, right? So it's chop gives the whole result. Okay, okay, Athanasius, Raku 1. So there is probably some comparison with memo eyes and without. So we're using memo eyes module, and there are like first index, last index from list. Wait, it's Raku, right? More utils. Right, so we take the number and suppress display of all the distinct combinations. Right, so init Fibonacci numbers. Init Fibonacci numbers is the function which takes the number and returns the array of integers. What? So this sums. If number is 0, if number is less than 2, we add this, we append this number to an empty array. Yeah, we create the array with this number. Otherwise, recursive cases. So we find the last index and the first index of the F Fibonacci. Where does it come from, actually? F Fibonacci. I believe it should be Fibonacci sums. Where do we feel that? No. Where? This one. Where do we feel this thing? We don't have it. Fibonacci number, right? But how do we create that? Init Fibonacci numbers. Okay. I was looking into an incorrect procedure, right? So init Fibonacci numbers. So we start with 1 and 2. So that's a shifted Fibonacci sequence. 1 to 1, 2 to 3. Okay. Cumulative sums. So Fibonacci is 2, sum is 3. So we initialize and we compute the next Fibonacci number. We append this to the array. We increment the sum, and okay, so this is the algorithm. I wonder why do we need this sum, or where do we use that? Cumulate. Okay, so we've got so we actually prepared two sequences here: the Fibonacci sequence itself and the cumulative sum. So which is the sum of all Fibonacci's numbers from the first up to the current one, right? Up to this number. It's a hash. Okay. Okay. So probably we can just immediately understand where we can start or stop. So the last index of the, so we are taking the Fibonacci thing. We find the first index, the last index. So basically we find the biggest Fibonacci number which is not bigger than the input n. Then we're looking for the first number where the cumulative sum is also like ends close to n. Then for Fibonacci numbers between these, so it's minimum and maximum, and those are indices, right? We start, we can actually use 3 dots here and swap min and max, I believe, right? Instead of doing reverse. But nevertheless, so this is the Fibonacci number. Previous term, find Fibonacci sum. New terms, previous term, we push this. If f is not, you see here, Unicode characters, is not on this. What is that? Terms. Yeah, this is the current previous terms and append. Okay, so I don't understand that. So find fib sum is actually a recursive call to the same function with the number which is from which we subtract the current f, right? The current Fibonacci number starting from the beginning one, from the bigger one. Okay. And after that, so we found this, and we then just display the results. And let's look briefly at these display results. So the number of elements, and there are different cases with plural stuff in the end. Okay. But let's run this, right? Raku, Athanasius, Raku. 1 1000. Ah, yeah, I don't have these things, and probably no. I think so. We need to dev install. We have, I think, already have this memo eyes module, and we can install this one. Actually, when this dev function, dev tool works, it works really good. And actually, I don't remember when it didn't work. Yeah, to be honest. So more utils. I believe this is the thing from Perl 5 converted to Perl 6, and now it's Raku module. Probably, I just don't understand why we need this first and last index. Can we use just the first method with the k, column k argument? Right. It's a bit slow, but okay. Let's go next. The next is solution by Colin Crain, Raku number 1. Raku number 1. Here is the solution. So we take the number with the default 9998. Fibonacci, the beginning of the Fibonacci sequence, actually it starts with 0 here, while the last two things, the sum of the last two elements is less or equals than, well, if it does not exceed the target, then we take the number as the sum of this, right? Basically, this is repeating here. Right, so we generated the sequence using the loop, okay. And then we remove the first two. That's interesting. So we reassign the whole array to itself without the first two elements, right? Then output is the combination. Oh, wow, whoa, yo, that's cool. So this is what we saw. This is what we saw, and here you see. So there's race degree 200 batches. So basically, so we can. So this race. So there are two things: hyper and race. In hyper, you ask to make computations in parallel, but keep the original sequence, right? The original order. With race, you don't care about the order, right? And so you can. So this thing is actually, this is the pair degree arrow fat comma, what you call fat comma in Perl 8, right? But you can use this index. This is Raku, and you see. So wow, that's cool. So this colon is the colon thing instead of parentheses, right? But if you have two arguments, basically you can have this second column. Wow, I didn't know that. Okay, but maybe we can. Okay, so this is installed. We can run this, right? So it gives 15 different combinations, and here they are. Okay. Okay, let's run this solution for the existing settings. With the existing settings, Raku, Colin Crain, Raku 1000, for example. So yeah, this is this is fast solution. So yeah, but basically you can play with changing these numbers 2 and 200. So the number of cores, the number of batches, and see how it will change. Of course, you have to run it for bigger numbers, like at least 10,000 or maybe even 100,000. Going next, and we go to the solution by Laurent Rosenfeld, Raku number 1. The solution, wow, cool. But yeah, basically, so if this input number exists in the command line, the modified task, then we take this, otherwise default value is 30. Right, so we've got this Fibonacci sequence, then we try all different combinations, and right, so yeah, basically we print the combination, actually. Yeah, so probably this is about why this task is called modified task, so because we are printing the combinations rather than the result, the number of them. But yeah, this is actually a more interesting task. Raku, what was that? Laurent Rosenfeld, Raku 1, right, and 1000, and I believe 2, right. So yeah, and again you see, so as in my solution, so it was printed as soon as they are ready. Okay, good. Going next, Mohammad Anwar, Raku number 1. Here's the solution. So we take the number, which is a positive integer number, and just Fibonacci sum. Fibonacci sum is the first function which is called, and right, so we take the number, we generate some Fibonacci sequence up to the Fibonacci series So we start with 1 and 2. Yeah, that's a shifted thing. And we saw this something like that. So while the last two numbers, basically it's the potential next Fibonacci number is not exceeding this number, we take this number, right? And so we've got this sequence here in Fibonacci array. Fibonacci sum is the empty thing. So we start from 1 up to the number, and we stop if basically we consumed all the numbers in the sequence. Fibonacci combination, so we take the combinations. So that's again we start finding all the combinations of one element, of two elements, and up to this. Why actually this is number? So I think we can just instead of this sum, we can just use the lengths of this, right? Because we cannot have more combinations than there are different Fibonacci numbers. Right. So then we take the sum and push this number to the result if this is, and we're flattening the array because I don't know why, because we want it like that. Okay, right, so Raku, Mohammad Anwar, Raku Ch1, Raku 1000. No, I need it like this. Right, so here are the combinations. Good. Okay, going next. So the next is this one, and we have two solutions left after that. Ooh, it's a long story. So we start with the number. So we see, so this is a slash, so we can use it without a sigil. So inside integer, so say input, say output. So the bug. Okay, so combi Fibonacci sum is a class. Let's briefly just look at this. So this is the class, and in that class, so we create this with the target number, the target sum, all combinations. There's a method of all combinations, and after that we just print that, I believe, right? So yeah, well, we do something to print it nicely. Maybe we can just run it immediately just to see how it works. What's there in the output? Jeon Raku Ch1. Yeah, so this is the output. Yeah, but we see that the result is correct, and total 15 cases found. Okay, Roger Bell West. Roger Bell West. So yeah, there are two tests. The number 6, number 9, the possible representation of this number. Yeah, so what we do here, so we generate the array of Fibonacci numbers, which less than $n, right? That's a nice thing, actually. And finally, we just make the combinations. Yeah, so basically you don't need this, right? Because it's the default case, actually. So we start all the combinations from one number up to the total number of things, and write the combinations, and we grab that. Yeah, so the syntax is different. So we use a function, a standalone function, kind of the built-in function, rather than a method call. But yeah, that's up to you which method to use, and return output, and we check that, and I believe it will just work. Raku Roger Bell West, Raku Ch1 1000, and yeah, this 1000 was ignored because there are two built-in test cases. Finally, the solution Raku 1 by Ulrich Rieke. And here is the solution. So we take the number from the command line this time. Yeah, so we start this Fibonacci number. Yeah, okay, the pattern we just saw a couple of times before. And then all the combinations. This is the combination. So we see, so just the default arguments, no arguments at all. And we will get all the combinations, including combinations of one number, and the combinations of that includes all the input things in Fibos array. If this is the sum that we want, we just print that. Okay, so yeah, this is what I wanted to run. Raku Ulrich here, Raku Ch1 1000. Voila. Right. Exclamation mark. Okay, good. And that was actually the last thing in the solutions of this week's task number 2 about number 1 about finding the Fibonacci numbers that add up to the given integer number. So yeah, week 77, task 1. And yeah, see you next time. Goodbye.